Let's look at one more example. This example is a little different. Uh, Here we have a set of coins. Coins come in either 3-cent variety or 5-cent variety, and we want to show that we can pay any amount exactly as long as it's 8 cents or higher. So for example, we can do 8 cents as 3 plus 5, we can do 9 as 3 plus 3 plus 3, we can do 10 as 5 plus 5, and so on and so forth. Here is a proof by induction. The basis is the smallest case that we have to worry about, which is 8, and that is something that is clearly feasible because we can do 3 plus 5. Now suppose we have a way to make purchase of k cents exactly. That is our hypothesis. Our goal is to show how we can construct an exact way to pay k plus 1 cents. So what do we want to do? We want to change whatever way we have created to pay k cents, and we want to convert it to pay k plus 1 cents. So we can do this in two cases. One case is we have at least one 5-cent coin in how we paid k cents. If we have that, then we can take that 5-cent coin out, replace it by two 3-cent coins, and that will change it to 6 cents, and that means that the total would be k plus 1. Now if we don't have a 5-cent coin, then we have a small problem, but the good thing is if we have no 5-cent coin, then we must have used at least three 3-cent coins. That's because we are starting with 8. In 8 we have used a 5-cent coin. Anything more than 8, if I don't use a 5-cent coin, then I must have at least three 3-cent coins, and that means I can take those three 3-cent coins and replace it by two 5-cent coins, and that will give me k plus 1 cents. Note that again, when we did this proof, we didn't make any assumption about what k is. All we did was we split the argument into two cases as to whether the k cent construction had 5-cent coin or not, and then we pursued each case to its logical end, where we showed that we can construct k plus 1 cents. There is a variation of induction called strong induction. So the reason we have strong induction versus what we studied right now, it's called weak induction, is in strong induction, to prove that pk plus 1 holds, we can assume that pk is true. This is something that we already did even in the weak induction. But we can also assume that p of k minus 1 is true, p of k minus 2 is true, and so on and so forth, all the way up to p of 1 is true. Now, we are not going to do a lot of examples with strong induction in this class. The kind of problems we are going to study, weak induction should be sufficient. But you're more than welcome to use strong induction if it helps in any particular proof. So what helps with strong induction is that we not only are assuming pk is true, but we are assuming some other values are true as well, namely p of k minus 1, p of k minus 2, and so on and so forth. This is something that will come handy when we are going to talk about a recurrence relation, because by necessity we need to make assumptions about more than one p-value being true, but you can do that fairly naturally So I'm not going to go through specific examples for strong induction here. So let's recap. Uh, Let Pn be a proposition about integer n. We wanted to show that Pn is true for all positive integers n. To do that, we first showed that P of 1 is true. Then we gave a proof that if either Pk is true or all P1 through Pk are true, then Pk plus 1 is true. This proof must be valid for any integer k. I'm emphasizing this about 100 times so far. The reason I'm doing that is because most mistakes that I see with induction related arguments are where students assume a specific value of k, like k is 5, and you cannot do that. You have to do this proof for any arbitrary value of k.
We have reached the end of this module. This module I have split into two. So 41 is essentially continuation of the same thing. But at this point, I would like you to do the review quiz to see if you have understood things uh, that were discussed in this module.